You know, over the past 15 years, the railroad industry has made great strides in improving safety by working to avoid accidents and derailments. Research and development efforts from the Federal Railroad Administration, the Association of American Railroads, and the railroad industry have significantly contributed to this effort.
Looking at this chart, it is easy to see that their combined efforts have dramatically improved the accident rate over the last 15 years.
The industry and the FRA are committed to maintaining the momentum in further reducing derailments and improving safety. In 1994, 1,825 derailments were reported to the FRA, representing 68% of all railroad accidents. Now, these derailments caused the industry an excess of $125 million. Considerable savings can be realized by understanding the mechanisms that cause derailments and employing methods to prevent them. The FRA categorizes the multiple causes of derailments into areas like human factors, equipment failure of track or vehicle, and vehicle-track interaction. Now, this film will concentrate on the derailments that result from unfavorable vehicle-track interaction.
To understand the physics of a derailment, it is important to first learn of the various components that make up a railroad car. Each rail car body rides on a suspension system called a truck. Conventional freight car trucks include the bolster, two side frames, a suspension system, and the axle wheel sets. A freight truck suspension, like the one shown, typically uses friction or hydraulic damping in parallel with a coil spring arrangement to control the ride quality of a car. Passenger train suspensions typically utilize rubber pads, airbags or springs, and hydraulic dampers. Both passenger and freight cars are subject to rare conditions of vehicle-track interactions that may result in a derailment. Factors that contribute to a derailment include rail car maintenance, track geometry, wheel-rail profiles, and train handling. There are two general types of vehicle-track interaction derailments: rail rollover and gauge spreading derailments, and flange climb derailments. Rail rollover and gauge spreading derailments usually involve loaded cars that generate large forces which act to spread the rails apart until the wheels drop between them, or the force causes the rail to actually roll over, causing a derailment. The potential for flange climb derailment increases when a rail car wheel generates a force against the gauge face of the rail greater than the load carried by that wheel. Under these conditions, the wheel may climb up the gauge face of the rail and derail. To better understand the forces involved, it is important to distinguish between these two types of derailment scenarios. Each involves different interactions between the rail car and track. When a rail car enters a curve, the truck should rotate under the car body. However, trucks don't always turn properly in curves. When the common three-piece truck does not turn properly, it may distort. This distortion, called truck warp, can force the wheel sets in the truck to run at a large angle relative to the radial line of the curve. This angle is referred to as the angle of attack. A wheel that runs at a large angle of attack no longer simply rolls on the rail, but rolls against the gauge face of the rail. Each wheel generates lateral forces in the directions shown. As the lateral forces increase beyond the strength of the rail to resist the force, the rails will spread apart or tip outward. If the lateral forces are large enough, then the rails may spread to the point that a wheel set falls between the rails or a rail rolls over. This results in a gauge spreading or rail rollover derailment. Let's examine the sequence of events that lead to such a derailment in more detail, to examine the factors that played a role in the derailment scenario. First, why didn't the truck turn properly in the curve? Two factors can cause this problem, either separately or in combination. The first factor is too much turning resistance between the car body and truck. The connections between the car body and truck are typically the center pivot and the side bearings. The center pivot, or center bowl center plate assembly, is usually a large thrust bearing that is supposed to allow the truck to rotate under the car body. However, if this connection has too much friction, then the truck will be difficult to turn. Problems that cause excessive center bowl turning resistance include the presence of rust and corrosion, mechanical interference from inadequate clearance, out-of-round components, broken center bowl liners or fasteners that project into the center bowl center plate area. Side bearing problems can also cause excessive truck turning resistance. Constant contact side bearings that are worn or improperly set up usually have a greater potential to cause excessive truck turning resistance. For example, if a constant contact side bearing is set up at less than its recommended height, it will apply excessive pressure to its wear plate. This can cause excessive truck turning resistance because the side bearing must slide on its wear plate for the truck to rotate properly. Another side bearing problem that can increase the truck turning resistance is protruding wear plate fasteners that interfere with the side bearing. Let's review the factors that lower truck turning resistance, like keeping center bowl friction low, checking center bowls and center plates for proper tolerances, checking for broken center bowl liners, inspecting the center bowl center plate area for protruding fasteners, checking for proper side bearing setup height, and inspecting the side bearing wear plate for protruding fasteners. Another factor that can prevent a truck from turning properly in a curve is poor steering. Steering refers to the forces that guide wheel sets and trucks through the curve. They are generated along the rails in the longitudinal direction. The picture shows steering or longitudinal forces in the proper direction to rotate the truck and align it in the curve. However, longitudinal forces can be generated in the opposite direction, such that they resist truck turning. This is referred to as poor steering. Several factors affect truck steering, including wheel rail profiles and track lubrication. The conditions which contribute to poor steering include worn wheels that have a hollow tread, excessive rail gauge corner relief from grinding, and the use of differential rail lubrication, where the outer rail in a curve is heavily lubricated while the inner rail is dry. Let's review the factors that will reduce poor steering, like avoiding excessive hollow tread wheels through replacement or reprofiling, avoiding rail gauge corner grinding that leaves excessive gauge corner relief, and providing effective lubrication to both rails in a curve. Research efforts by the Transportation Technology Center, the FRA, and the railroads are still investigating appropriate guidelines that would define condemning profile limits and provide the tools to measure profiles. The next event in the gauge spreading derailment scenario was truck warping. What caused the truck to warp? Several factors affect a truck's resistance to warping. First, a significant part of a truck's warp restraint comes from the snubbing wedges. Snubbing wedges, which slide easily, lower a truck's warp resistance. Factors which decrease snubbing wedge pressure include wedge wear and snubbing spring damage or fatigue. Different truck designs have different warp resistances. Snubbing pressures on variable damp trucks elevate as a car load increases, which provides higher warp resistances. Snubbing pressures with constant damp trucks remain constant as the load increases. Some truck components can reduce the warp resistance when they are applied improperly. Elastomer-coated snubbing wedges and elastomer-bearing adapter pads are intended to be used on specific truck designs and should not be improperly applied. An unsuitable application of these devices could potentially lower a truck's warp resistance. Gib clearances affect the maximum amount that a truck can warp. Worn gibs increase the maximum truck warp angle and the chances of a gauge spreading derailment. The lateral forces generated by a wheel set running at a large angle of attack increase with the wheel-rail friction. Most gauge spreading or rail rollover derailments are associated with extremely dry, low rail running surfaces. Some railroads are experimenting with lubrication on the running surface of the rail, especially the low rail, to reduce the effect of these large lateral gauge spreading forces. Let's review the factors that lower truck warping potential, like maintaining the snubbing wedges and springs for all truck designs, avoiding the application of elastomer devices in trucks where they were not intended, and maintaining proper gib tolerances. Two factors affect the maximum amount of lateral force that can be generated by a truck: wheel set angles of attack and the friction between the wheel and rail. But what happens after the truck warps? It generates a large angle of attack that increases lateral forces until all of the friction between the wheel and the rail is used up. In the derailment scenario, the rails were rolled outward and spread apart by these large lateral gauge spreading forces. What factors affect the roll or spreading resistance of rails? First, rail roll increases when a series of trucks warp and generate large gauge spreading forces. Some articulated rail vehicles have a greater tendency to spread the rails because they potentially have a number of successive warp trucks that can each produce large gauge spreading forces. Conventional cars, on the other hand, usually generate less gauge spreading force because a trailing truck that is steering properly will act to resist the rail rollover caused by a leading truck that is warped. For a conventional car that is curving properly, the lateral force pattern would look like this. However, if the trailing truck is warped or not steering properly on a conventional car, then it will act with the leading warped truck to produce high lateral forces that may potentially roll or spread the rail outward. Another factor that strongly affects rail rollover is the contact position between the wheel and rail. Compare the two wheel-rail contact positions shown. As the contact position between the wheel and rail moves toward the field side of the rail, the tipping movement applied to the rail changes direction to roll the rail outward. As you can see, wheels with false flanges have a much greater tendency to roll the rails than properly tapered wheels. This is the reason that some railroads are experimenting with beveling the field corner of rails and curves to avoid false flange wheels contacting the rails on the field side. Let's review the factors that can improve rail roll resistance, like paying close attention to truck maintenance on all rail cars, particularly those used in articulated designs, maintaining low friction center bowl connections, maintaining proper side bearing setup heights, and reprofiling or replacing wheels that develop hollow treads or false flanges. In the last segment, we described the gauge spreading or rail rollover derailment scenario. Now we will describe the low-speed flange climb derailment. A flange climb derailment shares many of the potential causes that lead to a gauge spreading derailment. In a low-speed flange climb derailment, at least one wheel set in a rail car must develop a large angle of attack. It is usually the leading wheel set in a truck that runs at the largest angle. The previous segment showed that a wheel set running at a large angle of attack can generate large lateral forces between the wheels and rails. This forces the wheel set into flange contact with the outer rail in the curve. At this point, some of the load carried by the wheel set may transfer from the outer wheel to the inner wheel. The reasons for this will be discussed in a moment. The transfer of load from the outer to inner wheel has two effects. First, the load pushing the outer wheel down on the rail is reduced. Secondly, the increasing load on the inner wheel increases the lateral force that pushes the wheel set into the outer rail. Eventually, a point may be reached where enough load is transferred from the outer to the inner wheel to cause the outer wheel to climb up and over the rail, derailing the car. The scenario first showed the wheel set developing a large angle of attack. There are several factors that can cause this problem. First, the truck may not turn properly in the curve and warp, causing both wheel sets to develop large angles of attack. Earlier, we said that excessive turning resistance can come from high center bowl friction, tight side bearings, or interference from fasteners. Let's review the efforts that will reduce truck turning resistance, like keeping center bowl friction low, checking center bowls and center plates for proper tolerances, checking for broken center bowl liners, inspecting the center bowl center plate area for protruding fasteners, checking for proper side bearing setup height, and inspecting the side bearing wear plate for protruding fasteners. Previously, we said that poor steering can resist truck turning. Several factors affect truck steering, including wheel and rail profiles and track lubrication. The conditions which contribute to poor steering include worn wheels that have a hollow tread, excessive rail gauge corner relief from grinding, and the use of differential rail lubrication, where the outer rail in a curve is lubricated while the inner rail is dry. Let's review the efforts that will help reduce poor steering, like maintaining worn wheel sets by replacement or reprofiling when necessary, avoiding rail gauge corner grinding that leaves excessive gauge corner relief, and providing lubrication to both rails in a curve. Earlier, we learned that several factors affect a truck's resistance to warping. First, a significant part of a truck's warp restraint comes from the snubbing wedges. Snubbing wedges, which slide easily, lower a truck's warp resistance. Factors which decrease snubbing wedge pressure include wedge wear and snubbing spring damage or fatigue. Elastomer-coated snubbing wedges and elastomer-bearing adapter pads are intended to be used on specific truck designs and should not be applied improperly. An improper application of these devices may lower a truck's warp resistance. Gib clearances affect the maximum amount that a truck can warp. Worn gibs increase the maximum truck warp angle and the chances of a flange climb derailment. As stated before, lateral forces generated by a wheel set running at a large angle of attack increase with the wheel rail friction. Most flange climb derailments are associated with extremely dry, low rail running surfaces. Some railroads are experimenting with lubrication on the running surface of the rail, especially the low rail, to reduce the effect of these large lateral forces. Let's review the efforts that improve truck warp resistance, like maintaining the snubbing wedges and springs, applying elastomer devices to only the truck designs where they are intended, and maintaining proper gib tolerances. Another factor that can increase the angle of attack of the wheel set is track alignment. Flange climb derailments are often associated with track that has an alignment kink. The rapid increase in curvature at the kink makes it difficult for railcar trucks to properly align themselves with the track. As a result, the wheel sets can develop large angles of attack. Thus, it is critical to maintain proper track alignment to help reduce the chances of a flange climb derailment. Large lateral wheel loads can also be generated by in-train forces. Consider this train, which is in a heavy buff condition from braking in a curve. Large buff forces are transmitted from one coupler to the other in a train. The buff action generates a force in the lateral direction against the outer rail. The greater the coupler angle, the larger the lateral force. This force is reacted between the wheels and rails. The lateral force reaction may be large enough to cause the outer wheels to climb the rails, especially if the wheels are already at a large angle of attack to the rail. Additionally, a run-in is a shock wave of force running through the train via the car bodies and couplers. It has two effects. It generates lateral forces due to the coupler angles, and it will tend to unload where the coupler height mismatch exceeds government and industry standards. Coupler angles are generally largest between long cars. However, a short car-long car combination has historically been shown to react to lateral forces generated by in-train forces. Let's review the factors that minimize undesirable reactions from in-train force, like effective train handling that controls large run-ins or run-outs, ensuring that coupler heights are within regulatory limits, and following your railroad's train makeup rules regarding long car, short car combinations. The next event in the flange climb derailment scenario was the transfer of load from the outer wheel to the inner wheel to the point where the outer wheel climbed over the rail. What factors contribute to this load transfer? In general, wheel load transfer at low speeds can be caused by one or more of these factors: poor load equalization, excessive track twist, and dynamic roll. Poor load equalization results in the wheel loads varying from wheel to wheel. This can be caused by several factors. First, the car body may be twisted, causing a shift in wheel load from one side of the truck to the other. Second, the side bearings may be set up improperly, causing a similar effect. Broken or missing truck bolster springs can also cause unequal wheel loading. Efforts that reduce the chances of undesirable wheel load transfer include repairing twisted car bodies, maintaining proper side bearing setup heights or clearances, and replacing worn or broken bolster springs. Track twist or change in cross level causes the rail to fall away from the rail car wheels. As a consequence, wheel loads will decrease on the side of the track, falling away from the truck, and increase on the other side. The amount of wheel unloading will depend on the rate of track twist and the ability of the rail car to accommodate the twist. The wheels of torsionally stiff rail cars like tank cars and covered hoppers will unload over lower track twist rates compared to torsionally soft rail cars like flat cars and gondolas. Track twist is usually associated with curved spirals. However, the track will twist in any areas where there is a change in cross level. Curved yard tracks and turnouts are areas that often exhibit excessive track twist. The rate of change in track cross level should be controlled to avoid problems with wheel load transfer associated with track twist. Finally, wheel load transfer can be caused by dynamic roll, which is a side-to-side rolling motion of a rail car. Dynamic roll may result from periodic staggered cross-level changes in the track. These cross-level changes are usually associated with jointed rail track, but may also occur in track with soft ballast or subgrade. If the spacing of the cross-level perturbations and the rail car speed coincide to a critical condition, then complete wheel unloading or wheel lift can occur. In this case, a small lateral inward force to the opposite wheel in contact with the rail can cause a wheel set to climb the rail. Excessive track cross-level variations should be avoided by properly maintaining the track cross-level geometry, especially in jointed rail track. In the rail car, undesired vertical motions are controlled by springs and snubbers. When operating over vertical track deviations, the snubbers control the rail car response. Worn friction wedges or faulty hydraulic shock absorbers will reduce the effectiveness of controlling vertical rail car response. To preserve control, it is important to maintain all snubbing devices in springs. In the low-speed flange climb derailment scenario, the combination of an increasing lateral force and a decreasing vertical wheel load reached a condition where the lateral force overcame the wheel load and caused the wheel to climb up the rail and derail. The wheel climbs the rail through friction. A lubricated rail will be more difficult to climb than a dry rail. Also, a shallow contact angle between the wheel flange and the rail will allow the wheel to climb at a lower lateral force than compared to a steep contact angle. The risks of low-speed flange climb derailments can be reduced by lubricating the rails and maintaining acceptable wheel-rail profiles. Let's review the factors that will reduce the chances of poor load equalization during operations over irregular track, like repairing car bodies that are twisted, avoiding excessive cross-level variations that cause undesirable track twist, and maintaining snubbers and springs in the truck. The dynamic flange climb derailment scenario is similar to the low-speed flange climb derailment scenario, except that the increase in lateral forces and wheel unloading are also affected by higher train speeds. Such potential derailments may result from rail car hunting at high speeds. Rail car hunting refers to the unstable lateral vibration of the rail car trucks at higher speeds. The wheels in the trucks move from side to side in a rapid lateral motion. The rapid lateral acceleration of the wheel sets causes them to generate short-duration lateral loads and a rapid transfer of the wheel load from one wheel to the other. If this unstable motion becomes severe enough, the wheel set can climb the rail and derail the car. Hunting instability is affected by several factors, including train speed, side-bearing condition, truck wear, and wheel profile shape. In general, hunting becomes more severe with increased speed. Constant contact side bearings help to control hunting in some rail car designs. Improperly set up or worn constant contact side bearings will allow the rail car to hunt at lower speeds. The snubbing wedges in trucks also helps to control hunting. As these wear or their springs fatigue, hunting will become more severe. Finally, worn wheels with a high conicity profile are much less stable than properly profiled wheel sets. Let's review the factors that control hunting, like following car speed restrictions, maintaining constant contact side bearings to the proper setup height, maintaining the snubbing wedge system in trucks, and reprofiling or replacing worn wheels, being especially mindful of rail cars that operate in higher speed service.
We've covered just a few aspects of unfavorable vehicle-track interaction. Surely there are many other factors that can potentially lead to derailments. However, our combined efforts will only enhance the safety performance of the railroad industry.